Welcome back, everybody. Today we're going to be talking about telescoping series. So telescoping series are best illustrated with an example. And here we have our example. And there are three key things to note about this scenario, or this case of series. The first thing is that, well, it's quite long. So you're not going to want to add this manually or even with a calculator. It will take too long. You're going to want to find a clever method to do this in a more efficient manner. Second thing we need to realize is that the denominator is not just one number. In fact, it's two numbers being multiplied together, and another special thing is that of the two numbers, one is one integer value greater than the other. So 4 is 1 greater than 3, 5 is 1 greater than 4, and so on. Alrighty, so what's the clever method that we're going to use? Well, it's called partial fraction expansion. That's partial fraction expansion. So what is this method? Well, let's look back at what we just mentioned, which is that each of the two terms in the denominator, one is always one integer value greater than the other. And this is the same for all the way through. So that means we can come up with a general formula for each of these terms. What is that general formula? Well, it's going to look something like this. It's going to be 1 over n times n plus 1, the quantity n plus 1. Alright, right, this is representative of each of these terms. If you substitute 3 in for n, then n plus 1 is 4, and you're going to get 1 over 3 times 4, and this is the same for the entire series. Okay, now what does partial fraction expansion tell us? Well, it tells us that we can write this general term as something like this. So we are essentially writing the general term as a sum of two fractions. Now these two fractions are unique in that their denominator, each of their denominators corresponds to one of the two numbers being multiplied together in the denominator of the original formula. So in this case it's n times n plus 1. So over here the two fractions, one will have the denominator n and the other will have the denominator of n plus 1. So what are these two things up here? These are two undetermined coefficients. And in order to do this expansion, we're basically going to have to solve for these coefficients. Now, how do we do that? Well, let's just start off by multiplying both sides by n times n plus 1. So here on the left side, we're going to have 1, right? Because if you multiply 1 over n times n plus 1 by n times n plus 1, you're going to get left over with 1. On the right side, though, it's a different story. A over n times n plus 1. Well, the two n's cancel out, right? But you're still left with an n plus 1. So you're going to have a times n plus 1. And on this side, it's kind of the opposite, right? Because you're multiplying this by n times n plus 1, but in this time, the n plus 1's cancel, and you're left with n. So you're going to get bn. All right, well, how do we solve this? Because it still doesn't look very solvable. You got 3 variables and only one equation. Well, we can also do something clever here. If we substitute 0n for n, we get to cancel out this entire term, and we get to cancel out the n, and you're only left with a. So you can actually solve for a. So let's do that. So if we let n equal to 0, then this equation becomes 1 is equal to a times 1, because 0 plus 1 is 1, and 1 times a, it's just a then. And this is 0, because the 0 times b is 0. Okay, so we get here that a is equal to 0. Or no, a is equal to 1. Alrighty, now let's try setting n equal to negative 1, because in that case, this entire term would cancel. So 1 is equal to 0, because negative 1 plus 1 is 0, and 0 times a is 0, plus negative b, right? Because n is going to negative 1 times b is negative b. So in this case, b is equal to negative 1. Alrighty, and that means we can write this formula as 1 over n times n plus 1 is equal to be 1 over n minus 1 over n plus 1. Alrighty, let's see how this applies to our series. So I've rewritten our derived equation here. So let's substitute in n equal to 3, right? Because if we substitute n equal to 3 here, we got this term. So we can just substitute n equal to 3 to the right-hand side, and we should be able to get our result previously. So we have 1 over 3 minus 1 over 4. Now, is this actually equal to this term? Well, we can check. What's 1/3 minus 1/4? Well, let's find the common denominator. That's 12, right? So we're going to multiply this numerator and denominator by 4 and this numerator and denominator by 3. So you're going to get 4 over 12 minus 3 over 12, which indeed is 1 over 12. Okay, let's keep going. So that means 1 over 4 times 5 is going to be equal to 1/4 minus 1/5. All right, 1 over 5 times 6, that's going to be equal to 1/5, or sorry, 1/5 minus 1/6. And 1 over 6 times 7 is equal to be 1/6 minus 1/7. Now this is going to keep going on until we get to 1 over 99 times 100. That's going to be equal to 1 over 99 minus 1 over 100. Now clearly there's something happening here. You're getting that each second term of each one of these terms cancels with the first term expansion of the consecutive following term. So negative 1/4 cancels with 1/4, negative 1/5 cancels with 1/5, negative 1/6 cancels with 1/6, negative 1/7 will cancel with the next term, which is 1/7, and so on until you get to the last term, because the last term will have to cancel with the next term, but the next term does not exist, right? Because it's always the negative term that cancels with the next positive term. So the last negative term does not cancel, but the positive term before it will cancel. So basically everything cancels in between, and you get that the entire sum is equal to 1/3 minus 1 over 100, which, if we do the math, is equal to 100 minus 3 over 300, which is equal to 97 over 300. So that was far, far easier than adding, okay, 1/12 plus 1/20th plus 1/30th plus all the way through 1 over 9,900, right? So this is just a convenient method of adding up these series. And the reason it's called telescoping series is because if you think about it, a telescope, try to do my best to draw one over here. Can be folded up, right? It can be folded up into a smaller, more compact version of itself in order to save space, right? And that's what this is essentially doing, because each one of these is being canceled out, so the entire series kind of just compresses into 2 terms. So that was telescoping series, guys. I hope you enjoyed, and I will see you in the next video.